In the previous episodes of this series, I covered virtually everything of note that there is to cover regarding the fire mechanic in the BFME games and the overhaul to it in the Age of the Ring mod. But there is one last thing I'd like to point you to. There is a little known recording of one of the devs of the BFME games back in the days when they were developing these games discussing these mechanics in detail, which has some fairly insightful aspects to it. Great for any fan of BFME who wants to know some fun details of the making of these games. You can find this at gdcvault.com, a great site for all kinds of audio recordings of professionals discussing anything under the sun, with a pretty considerable backlog of entries. This presentation is by Martin Hoffesommer for the company Electronic Arts Los Angeles from way back in the BFME2 development days. So without further ado, I'll let him tell you all about it.
All right, I think we're ready to start? Okay. I've been reminded to tell you, please turn off your cell phones, pagers, everything else. And at the end of the session, if you would please turn in the review form filled out, hand it to somebody at the door, it'd be nice. Thank you. So, this is the talk about Battle for Middle-earth is Burning. Fire is a gameplay element. My name is Martin Hoffesommer. I am the lead engineer on the first part and the second part, BFME2. The agenda for today, and I hope everybody can hear me okay. I'm going to talk a little bit about the history of the engine we used, a little bit about the background, and a little bit about the special challenges when it comes to adding new major features into the existing code base, especially when you're talking about a system that's been around for, well, quite a number of years. I'm going to go into the fire as what the feature requirements were, what design wanted out of it, and what the implications for us on the engineering side were. The design side. Then we went about how we prototyped the actual feature, what worked, what didn't work. I'm going to talk quite a bit about the actual implementation. So one of the takeaways actually for you guys will be an almost working system if you want to do things like we did or similar effects. Well, it says demos here, but it's videos actually, so bear with me. My laptop is unfortunately not capable of running the game for whatever reason. A couple of conclusions and things going forward for, well, potential future titles. And of course, quite a bit of Q&A time at the end of it. So, a brief history of SAGE, and if anybody asks me what SAGE stands for, I have to tell you off the record what it is, because I can't repeat this out loud here. SAGE was first used in Command & Conquer Generals, which was shipped in February 2003. Then that code base was taken for Command & Conquer General 0 Hour, shipped at September 2003 as an expansion pack. And finally, in Battle for Middle-earth in December 2004. After that, we went for Battle for Middle-earth 2 using the same code base, and this time actually without fake screenshots. Sorry about the picture I stole from GameSpot. I couldn't find any good pictures on my own page, actually. So we started this one early in 2005, and initially was planned as a Battle for Middle-earth 1 expansion pack. So scheduling was actually accordingly. And it was changed to a full SKU with a major increase in scope during March, April. And I think we got an additional 6 months to finish the full title. Well, we shipped in February 2006. This time actually without Insane Crunch. You might have heard a little bit about the disaster on BFME1. ESPOUS. That was us. But the major point, or one of the major points when you look at this and the fact that we shipped essentially 4 major titles, or 3+1 titles with the same code base, is that there is a really, really huge merit in not starting from scratch every single time, but basically use what you have, strip it out a little bit when you're going the next iteration, and build from there. Unfortunately, it comes also at a kind of expensive price, and I'm going to talk about that a little bit more in the next slide. But first, let me show you a little bit about BFME2 in case you haven't seen it yet. And that was stupid. All right, just a second, bear with me here. Here we go. So I have to go here. All righty. Just by the way, this was all in-game footage, so we didn't do any special trailers for this. All right, code growth. So you can imagine if you have a code base that spans multiple years, multiple SKUs, that there is some craft probably accumulating, and things usually tend to get bigger, not smaller over time, especially when it comes to code. CNC journals had about 2,900 source files, about 40 megabytes worth, and about 720,000 lines of code. That doesn't count any comments or empty lines. By the time we're done with BFME2, we had about 8,000 files and about 1.75 million lines of code. By the way, that's about, from what I heard, about 25% of the code size of Windows XP. Is kind of embarrassing. The problem with that is, if you try to compile this, it takes a while. So even changing a single file and relinking takes about 5 minutes. A full rebuild takes about 45 minutes just for a single configuration. That's an insane amount of time. Now, if you're trying to come up with a new feature and you don't even know if the feature is fun or not, all you have is an initial idea, oh, let's do this or let's do that, you can imagine you have to do lots and lots of iterations. At the current rate of this year, you can do about, 20, maybe 30 iterations a day. That's not nearly enough to try out all these different things. And, I mean, what are the odds of coming up with a good idea, good implementation in the first 20 or 30 tries? It takes more than that. So, big problem there. But let's digress for a minute. Then we came with the feature requirements for Fire. So, Fire, cool. Always looks great, nice effect. But nobody's actually using it as a gameplay element. It's always just used as an after effect. It's mostly used to show, hey, there's some damage going on. Ooh, big explosion. But it's the result of damage being applied, not the other way around. It does not do actual damage. It doesn't spread, which would also be kind of nice. If you imagine you have some oil somewhere and somebody sets it on fire and it slowly spreads and sets everything else on fire and spreads damage in the process. So, yeah, would be a nice, cool feature. So, let's do gameplay Fire. Actually, that was the one-liner I got from production. Wouldn't that be cool? Yeah, but, of course, in a real-life scenario, new features, we can't really use much more memory for that because we're already stretching it as it is. We can't use much CPU, and hey, GPU, come on. I mean, we're trying to get all these other cool stuff in there. You can't really use much GPU for that as well. And, of course, it needs to work with all those 2 million lines of code that we already have. Problem. So, the initial idea, keep it simple and stupid. Let's try to make it work with the bare minimum, what we can do on the engineering side, to satisfy all the requirements from the production side and basically get away with it. In order to do that, we divided and conquered. So let's tackle the gameplay side first, and let's not care about how it's going to look on screen because graphics engineers, they're pretty good at that. They're going to figure out something really cool and nice looking. And especially for games based on the Sage engine, the separation between simulation and visualization is extremely important. The way we do our networking is by using distributed simulation or essentially lockstepping everybody. So every machine has to do the same simulation steps to come up with exactly the same results. It's like, I think pretty much every other major RTS does the same thing. That also means that no matter what machine you're playing on, whether it be the lowest, 1.3 gigahertz Pentium, or the fastest Uber 3.5, 3.64, whatever machine, they always have to come up with the same logic result. It can look different on screen, but it better not be different in the result as far as the actual gameplay is concerned, because otherwise you're going to get in a desync and, well, the game's over at that stage. So dividing and conquering, separating simulation and visualization was not only important from how to approach the problem, but also vital to actually make it work on all platforms that we're trying to support. So, on the gameplay side, the idea is, okay, the simples we could come up with is do something like Game of Life. Use a cellular automaton. And that is very, very simple concept. It is also a concept that is very easy to explain to non-engineers, which is also critical when you're trying to add a new feature. Because if you're just implementing a new feature and nobody but the engineers understand what's going on, it's really hard to get buy-in from production, from design, from anybody else. So we showed actually a Game of Life running in Java to some people and said, hey, something similar to that. Can you see how it's spreading, how it's moving around? Could you imagine that could be fire seeing from top? And they said, yeah, sure, that could be it, but can we try it out? How long does it take? That was not easy to answer at that moment, but I'll get to that in a second. So, the basic principle of Game of Life or any cellular automaton is you divide the whole map you have into discrete cells, and you add some very, very simple, some very basic rules that describe how, in this case, how a cell spreads from one point to the other or how it dies. So we took that and extended it for fire. A cell can be on fire or cannot be on fire. And we defined the rules for fire spreading. The authoring side, we have a tool called World Builder that ships with the game. It is a 3D tool for placing different objects on the map, for doing all the scripting in a visual environment. And it also already had facilities for marking terrain cells with metadata. And terrain cells is actually already something we can use also to tag the information if it's burning or not onto it. So in theory, we could use that and just add another variant of that paint tool to say, okay, how can fire spread in this area? Is that something that can easily catch fire, or is it something that's really hard to set on fire? One of the things design really wanted, they wanted control over how fire would spread. I think the biggest fear they actually had was, oh my God, so I'm going to shoot this single arrow into a forest, and the whole thing is going to go ablaze, spread across the whole map and kill everything? That's just way too powerful. We can't have that. So we had to basically get buy-in from design. We had to make sure that their fears were addressed and show them, hey, that's not going to happen. We can control this fire. And by the way, this is a screenshot of World Builder. These are different flammability areas. This one, for example, would be a grassy area. These areas are highly flammable. And actually, as it turned out, we only had two different areas besides the non-burning areas, those here. Initially, we thought there would be more, but we actually got away with two different types. Prototyping. That was the key to how we actually made the whole system work. First of all, it allowed us to make sure that whatever we came up with as the implementation would actually work as designed. So would the fire actually spread across the whole map, or wouldn't it burn at all? Would it just spread too slowly, too fast? Would it exhibit all the different behaviors we wanted out of it? So we expected lots of failures, lots of changes, but the high turnaround times and changes actually made it prohibitive to do the prototyping in-game. And the additional problem was communication with design and production. It would have been nice to do it in-game, but if you need 5, 10, 15 minutes for a single iteration, you can imagine that's not really a viable solution. So we used an actual prototype, and we actually used a standalone prototype. And I'll show that actually in a minute. It was started from scratch. It was really, really ugly. And it was only implemented in what was needed. It actually had programmer art in it, so definitely not pretty. The whole implementation itself took only 2 days. And that included figuring out what to actually do. So from the point in time where Mike Verdu, our producer, said, hey, we need fire, to actually having something on screen and something you could play around with took 2 work days. And I'm talking 2 8-hour days, not 2 16-hour days or something crazy like that. Nobody would do that. The turnaround time for a change in this kind of code base was obviously in the 1 or 2 second range, which is really, really nice. Authoring in the prototype, well, That's the authoring. Use a text file, simple INI, and all the data you were trying to manipulate, put it in the INI file, give somebody text editor, muck around with it. Not pretty, but it gets the job done, and that's what it's all about. It's about trying out things, and hey, if it doesn't work, throw it all away, start from scratch. It was only a day or two. No huge resistance against change. And if you're trying to make something new, something fun, making sure that you can throw something away without having a bad conscience is always a good idea. Now I'm going to get into the actual implementation quite a bit. So we're using a regular grid of cells, and each cell has 4 properties. I'm going to explain those actually. We introduced the concept of fuel, which is just the amount of burnable stuff that is in a given cell. You can think of it as how much gas is in a cell. Something that can burn away, and when there's nothing more to burn, it just doesn't catch fire because there isn't anything more in it. The burn rate, which defines, okay, in any given time slot, how much of that fuel is actually burning away. And for gameplay reasons, we also capped it at a maximum level to make sure that we don't have anything that burns and burns and burns higher and higher and higher until it just kind of explodes. Maybe similar to a physics system where you have an integrator that just spins out of control and brings the whole system down. We just capped it at that. A decay, which is a value that we subtracted from the burn rate at every update to make sure that fire over time would slowly but gradually fade away. To make sure, basically we're trying to build into the system the behavior design wanted, which was, yeah, we want fire, we want it to spread a little bit, but not much. Just put the arrow in there, have it spread a couple of cells, let it burn for a couple of seconds, but then please let it go out again, because we don't want it to be all powerful. After all, this feature was designed to be a secondary effect and not a primary power like anything else in the game. And the last property of a cell is resistance. And resistance, I have to explain a little bit more. It controls how fire is spreading. Essentially, it means the higher the resistance of a cell is, the less likely it is that fire spreads into this cell. You can think of it as fire safety, essentially. I'm going to explain resistance on a separate set of slides because it's a little bit more difficult to understand. So, a simple example, we have a cell on fire and it has a decay of 5. So, at the first time slot, the burn rate is 20, it's already on fire through whatever means, and we have 50 units of fuel left over here. We're going to do one update. The burn rate goes down by 5 because the decay of 5 decreases it by 5. And we're going to take this burn rate, this 15, down from the fuel, down to 35. Rinse and repeat. We get to 10, 5, and eventually the cell stops burning because the burn rate reached 0, but there's still fuel left. So the next time somebody shoots that cell with something that burns, it would catch fire again and would still burn until actually there's no more fuel left or the burn rate hits 0. Spreading the fire, that's actually where it gets really interesting because a single cell on fire isn't that much fun. Looks nice, little flickering flame, but then it goes out again. Great. So the resistance value controls if and how fire spreads to neighboring cells. During each update cycle, after we adjust the burn rate by the decay value, and the fuel has been used up, like I showed in the previous slide, I'm testing all direct neighbor cells, and this is where it's similar to the game of life, where the neighboring cells influence what's happening with the current cell. If the burn rate in one of those neighboring cells is higher than the resistance of the cell we're currently looking at, we're adding the difference to the burn rate of the cell. Have I lost everybody now? Good. I got a whole set of slides explaining this in very much detail. It's a very, very simple concept. It's a very simple rule that defines how cells spread the information to neighboring cells, but it's actually all that's needed to make the whole fire system work and get all the behaviors out of it. And I'll show this all in the prototype. It's very simple. So, the implementation looks like this, a single update. First you apply the decay to all the cells, then you burn the fuel down, and then you spread the fire to all the neighboring cells. Rinse and repeat. And by controlling how often you run these updates, you have direct control over how much CPU you use. Remember, one of the key requirements was low CPU usage. And because we want fire to spread slowly anyway, we don't have to do the updates all that often. All right. Now we go for an actual example. We have two cells, cell A and cell B. Let's assume they are directly next to each other. Cell A has a resistance of 100 because I don't want it to catch aim of fire. Cell B has a resistance of 27. And both have a decay of 5. So first, as I said before in the update slide, first we apply the decay, which means we're going to reduce the burn rate in A from 20 down to 15. Down to 15. The next one is we're going to burn it down. And since only A is currently burning, only the fuel in A will reduce by 15 down to 35. B will not change because, well, it's not on fire yet. The next step is spreading the fire. B has a resistance of 7. And because A, as a direct neighbor, is currently burning with 15, well, 15 minus 7 is 8, so we add that to B. So B is now suddenly on fire, caught on fire by being next to A and having somebody next to him that has a higher burn rate than the current resistance. So now we just do another rinse and repeat step. We decay. This time we actually decay both because B is on fire as well. So A is down to 10, B is down to 3. Burn down both cells independently. And another spread. And because A is still more than 7, we have another 3 left over we add to B. So B actually keeps on burning a little bit longer than it would have had originally. Rinse and repeat. Burning down until we eventually hit 0 for both. So now I'm going to show the prototype. And please bear with me, this one is really ugly. It's programmer art. And it's going to be a little bit difficult because of the setup I have here. Pretty, ain't it? So this is our map. All the cells here, and the number in here is the current burn rate. I'm going to load a scenario. All these scenarios are just the simple text files like I had on the previous slide before. So the first scenario is we're going to shoot an arrow just into grass. And the desired behavior here is to not have the whole grass plane catch on fire and spread wildly. This is where the arrow was shot. You see a little red area here that signifies, okay, it's currently on fire. Everything else currently not on fire. And then I can do simulation steps here. You see the neighboring cells start to spread on fire. This one cools down because of the decay rate of grass cells. But ultimately it goes out. Nice. Just what we want. So let's try something else. What if we change the resistance value of the grass? Right now it's a pretty high resistance because we don't want fire to go wildly across the grass plains. But what if we lower the value? So exactly the same scenario. Only difference is the resistance value of the grass is lowered, I think even down to 1. And as you can see, the fire actually spreads more and more. And we get exactly what the designers were afraid of. Okay, probably not a good set of values for this one. This is also another grass example, but this is shooting a catapult projectile into the grass, which burns much, much hotter. And we want it to spread a little bit further than just a little arrow. But we still don't want it to catch the fire. So I changed the resistance value back to the original one, where we have the desired behavior of the fire going out. And now I'm trying out what happens if I shoot something in there that's a little bit heavier, a little hotter than just a single arrow. And it does spread a little bit more. It actually burns, but yep, it actually goes out as well. But it leaves more of an area burned off, which is actually a very nice behavior as well. So the next scenario. This is actually shooting an arrow into an oil field. So one of the things we added for the game for one of the heroes is the ability to spill oil as it walks around. And you can then later set that oil on fire, which is actually kind of fun to do. I'll show a little video of that later. But first, before we wanted to add that feature, we wanted to make sure, hey, can we actually do this with all the other values in there? So these little star areas here are oil. This is a little oil field, a little oil patch in the grassy plain here. And we have one arrow shot in there. Let's see what happens. And as expected, it burns. It burns actually pretty hot. The more intense the red gets, the higher the burn rate is to signify the intensity of the fire. But if you look in the areas surrounding this oil field, it does catch fire, but after a while it goes out again, which is very similar to the behavior we saw with the catapult projectile before. So also desired value. Now let me just point out, these values I have in here took about 3 to 4 hours to figure all these values out, to find a good set that works in all the scenarios we wanted to, and exhibited all the desired behaviors and none of the undesired ones. So the last one is actually, we shoot a catapult projectile into a bunch of trees. Trees or objects in general have the ability to modify the flammability of the ground beneath. So just by placing a bunch of trees in a world builder, you essentially create something that's burnable, even though the ground beneath it might not be burnable. And it's actually similar to the oil scenario before. You see the trees themselves actually catching fire, or rather the cells where the trees are on catching fire, but nothing else. So they'll burn down, nothing else burns down. Actually, this was a little bit too extreme. We had to tweak that back down because design didn't want a single projectile to burn out a whole forest. It was a little bit too much. All right, on to the implementation once more. The actual implementation uses sliced updates. As it turned out, updating the whole map, even though it was just a minor CPU hit, about 1 or 2 milliseconds, it's still causing some glitches every now and then if you just run it once every second or every 2 seconds. So instead, in the actual implementation in the game, we decided to do sliced updates. One slice, every single logic update, and the whole update cycle lasted 10 logic frames, which is about 2 seconds in the current implementation. To show a little bit, anybody see this? It's not my program. Okay. All right. Let's see if we can continue where we left off. I wasn't stressing PowerPoint that much now, was I? There we go. Okay. This is actual source code from the actual implementation in the prototype. It's all very, very straightforward, very simple source code, but it was designed to be that way. Because you don't need to get extra complicated just to get a feature up and running. The simpler you can do it, the better you're off, because let's all be honest, I mean, things get complicated just by themselves. So the implementation, first we run through the whole grid, and only for the cells that are currently burning, which is the fuel burn rate here, we apply the decay. And if the burn rate actually went to 0, which means the fire's off in that cell, we don't even bother with it anymore and just skip it. Otherwise, we burn up the fuel here as well. And if the fuel reaches 0, we also tell it, hey, you can't burn anymore because there's nothing more to burn left, so stop. Then after all these cells have been updated in a single pass, we spread the fire. So for each cell, once again, only for the ones that are currently burning. Only the ones that currently have fuel, we actually look at those. If a cell doesn't have fuel, we don't even look at burnability because it wouldn't have made any sense anyways. We look at the resistance value of the current cell, and now these are the neighborings. So this is the left neighbor, the right neighbor, bottom, and the top one is on the next slide. If the current burn rate of that cell is higher than our resistance value, we add the difference between the two to a temporary value here, which will then be added to our current, will be set to our current burn rate here. And here's the cap with the maximum fuel burn rate, which, as a kind of a stopgap solution, made sure that nothing gets too hot. Without this, and the initial implementation actually didn't have this max fuel burn rate in it, we ran into scenarios where, for example, if you shoot this catapult projectile even into some simple grass, it would still spread like wildfire, no matter what you set all the other values to, just because it would burn so hot you couldn't stop it. And if you set the values to actually make it stop, you couldn't get any desirable behavior out of just shooting the simple arrow in it anymore. So this was kind of a stopgap solution we had to come up with actually during prototyping. And finally, after all this, the new burn values have been calculated, we copy the values over into the actual burn rate. We have to do this in a couple of phases because, well, that's just the way how it works with going over grid multiple times. On the damage side, I mean, having all this fire burning logically is all nice and good, but gameplay fire wouldn't be gameplay fire without actually causing some damage. So for actually tying it into the existing system in the game, we used the existing damage model. We're remembering how much fuel was burnt away in a given update cycle. For example, if a cell used 15 units, then, well, we remember that 15. And this value of 15, we actually pushed down the pipeline into the object on that cell and told it, hey, you got a damage of 15 with damage type fire. And that was just another damage type, similar to, for example, pierce damage or wedge damage or magic damage. So it could be modified by the designers in the way that we're used to, with different armor sets, weapon sets, and all the other things. Very nice, very easy for them to control. Things we discovered during prototyping, well, already mentioned the fact that we needed to cap the current burn rate of a cell with kind of a kludge of max burn rate. But also on top of that, we had to limit the total number of cells on fire as a whole, just because we couldn't completely eliminate the fear of designers, hey, what if everything's on fire and the frame rate goes down and it's just too much going on? So we said, okay, fine. Let's limit it to an arbitrary number and see how it goes, and we actually kept that number in there. Something else that was not discovered during prototyping, but actually during the game was, okay, so now we get everything in-game, and it all works nicely, it looks good and looks cool, but after 5 minutes of gameplay, nothing burns anymore. Why is that? Well, because you already burned up all the stuff there, that's why. So it doesn't regenerate? Nope. So that was something we didn't discover because, well, nobody was playing the prototype for 5 minutes. It's not that much fun to play. So we added a so-called fuel regeneration rate that basically tells the system, okay, if the fuel level in the cell is less than the initial original value and is not currently burning, slowly but gradually get it back up to the normal level over the course of a minute or two. The visualization side, and I apologize for kind of skimming on that, but that's the main reason I'm skimming on this is because I didn't do it, so I'm not at liberty to talk much about it. It was implemented by Vishwaranjan, and he was using a GPU particle system done by Lutz Latter. He presented actually last year in GDC 05 about GPU-based particle systems. What we did for this is we used the list of cells that are currently on fire as an input into a video texture-based particle system. Essentially, every cell that currently has a burn rate will have a little particle on that position. And if it goes out again, it's removed from the active list and the particle goes away at that spot. And it actually turned out to be enough. Initially, we also tried modulating the intensity of the particles by the burn rate. Actually, that didn't turn out good at all. It just looked like crap. Either it wasn't showing up at all or was just showing up too hot. So just doing the simple on and off was more than enough. And in addition to that, Vishwa and Lutz placed scorch marks randomly on cells that are currently burning, and those will also fade away over time, basically making the area a little bit black, looking as if, hey, something burned off there. But because we're regenerating fuel, it also makes sense to remove those scorch marks over time to get back into a visually pristine situation. All right. Now I got a little bit of eye candy, a couple of videos. Those videos are consisting of in-game footage. They have mostly fire stuff in them. There are also some other elements in it. I'll point out some of the fire elements as it goes along. That is just brilliant. Okay, now let's do it this way. So this is a video showing the different superpowers of heroes in the game. This also contains the troll spreading oil as it walks around. First the worm, which has a really nice fire-breathing ability. You can also see guys that are dead. We kind of let them run around a little bit longer, just screaming and burning a little bit. Just, a little fun there. You can see over to the right the fire system. It actually goes out fairly quickly because all these cells are technically grassy cells, which are designed to go out pretty quickly. We're in a fire. Alright, that's scorching sun. You can see the cells going on fire here. And of course everything that stands on it catches fire as well. And this is a combination of logical fire, you see the ground burning, and actual just effects fire. And the dragon is breathing fire, that's just effect fire, classical way. Got a little bit more. Actually, the troll is in the next video, as it turns out. These are showing off some of the Create a Hero powers. We have a so-called Create a Hero system in the game where you can create your own hero and use from a palette of different magical powers in it. And one of them is the spill oil and set it on fire special ability. So here we go, the troll, and if you look closely you can actually see him spilling oil, splashing all over the place and actually dropping all these little oil dots here. Actually what's happening here is he's increasing the fuel amount in those cells and setting the resistance to almost zero. Visually we add the little decals there and then he waits for the guys and actually sets it on fire. He himself, of course, is has a high resistance to fire, so it doesn't take damage. The other guys, of course, kind of do. And then the last piece of video is actually showing off a little bit of Isengard. Isengard is all about fire. So Isengard uses a lot of different fire elements in it. Okay. So let me see if we can get back to PowerPoint here. Actually worked. So, in conclusion, stuff that worked, stuff that didn't work, because, well, big surprise, something actually didn't work. The prototype approach worked almost perfectly. We played around with the prototype for about 2 weeks, just on and off, trying different things, see how the values work, tweaking it, handing it off to design, talking to production, making sure everybody was signing off on it. Then we dropped the implementation into the actual game. Dropping it in took about a day. We could take most of the actual implementation in-game and then added interfaces to hook up the visual portion of it, to hook up audio, and all these other little tricks and required elements to actually make it fun in a game. Something that didn't work was the tie-in with AI. The tie-in with AI is poor at best. The biggest problem actually there is that the units themselves are not really aware of the fact that they're standing in fire, which actually makes them look kind of stupid. That was also the major reason why we actually toned down fire quite a bit more than we initially planned, to make them look less stupid. In an ideal world, we would have had a system in there that if a unit is on fire or is close to a fire, would try to move away, but that would also take away from player control. So in the end, we said, okay, let's keep the player control where it is and just tone down the fire a little bit more and figure out something else for the next game around. Something else we discovered, because it just wasn't in the prototype, was that we didn't have incremental updates in the prototype. We updated the whole map. Every time I press the plus button, we do a full map update. We discovered only later that the damage that we're dealing to units actually must be dealt on every update, and not just when you're updating that particular slice of the map. Because what was happening was you had units standing visually in fire, but because the slice wasn't updated at that particular moment in time, they weren't taking any damage. So you could actually have units seemingly walking through fire unharmed, just because, well, it just wasn't that time to get the damage. So what we did in the actual game was, okay, let's keep track of everything that's burning. We need to do that anyway for the fire to be visible, and deal that damage every tick to those units. Going back to AI, so we pretty much knew from the onset that having full AI awareness was out of the question, just given the nature of just having 12 months to do a full game. But I think going forward, that is something we can definitely look into and make more improvements. Also, something that worked really nice was the fact that using a very, very simple approach for this kind of design helped us focus on actually making it more fun. So something I think we'll see in the future is using more of these kind of cell-based approaches for field of area effects and new gameplay elements going forward. And, oh yeah, of course, keep it simple and stupid absolutely rules. So that's pretty much the end of the talk. Running a little short here, but I guess since booth crawl is at 5, we're good. And there might be a couple of questions, so I'm happy to answer anything that's coming up. So the question is was there automatic correlation between the texture used on the tile and how it actually reacted to fire, or was that something done completely separately? And no, actually it was done completely separately, because by the time the additional requirement for fire came up, we were already well underway, almost entering production phase, and we had tons of legacy textures. So we decided not to go back to the extra work and tagging all those textures with different flammability and just say, okay, since the prototype only had 2 or 3 different types we needed anyway to do what we wanted, let's just paint those and be done with it. In the back. How did the fire here terrain, how did that interact with burning buildings and things like that? Okay, so the question is, the fire visually is only on the terrain. How did it interact with anything else that wasn't directly the terrain, but objects standing on top of it? Is that it? It interacted in the way that, okay, so yes, the whole system is essentially a terrain-based fire system. But because everything that takes fire in our game pretty much, that takes damage in our game pretty much catches fire, it looks as if the fire from the terrain is actually spreading to, for example, an object standing on top of it. So we kind of cheated there. Yes? You given any thoughts to extending this into 3D? So the question is, have we given it any thoughts to extending it into 3D? Not yet, but I think it's a very simple, straightforward thing to do. It's mostly memory requirements, but if you reduce the resolution of the grid, for example, yeah, absolutely, you could do that. Yes. In the back. So if we had more time, were there any features we wish we could have added? AI, definitely. It was actually really, really painful for me to see that we had to turn down the fire system to the point of almost crippling it out of the game. It's still in the game, but it's not nearly as prevalent as I would have liked. And I think AI was the major reason why we didn't have it in there as dominantly as I would have liked to see it. So if we had more time, I would say AI awareness definitely on the top of my list. Absolutely.
Fire in old battle would be used a lot for visibility, such as seeing at night or creating a smoke screen. Do you think with more processing power, you can add more smoke effects and use smoke as a visibility gameplay element?
So the question is, in the old times, fire and smoke was basically used for increasing or decreasing visibility. And with the trend of having more and more CPU power available, would it be feasible to use these kind of features in upcoming games as well? Yeah, absolutely. Absolutely. I can definitely see that happening. There is an expansion pack planned, from what I heard, but I don't think we're going to be directly involved in it.
Did you put any thought into using the same algorithm using the terrain to might have fire spread between units?
So the question was, have we given any thought to using the system for spreading fire in the terrain into spreading fire between units? What we actually thought about, and we took it out for the AI reason, is wouldn't it be cool if you had a unit that, if it is currently burning, would set the cells it's running over on fire? We actually had that in there, but the result of that was you set an area, you shot like a flaming catapult ball into a bunch of guys. They would catch fire. They'd start running around, run to the forest, and the whole thing suddenly went to place. It looked totally cool. It was really fun playing with it, but it kind of defeated the purpose of keeping it secondary power.
Question. Your algorithm was a straightforward algorithm. Did you consider a random element to it to dial down the chances of something to catch fire?
So. Right. So the question was, the algorithm itself is very straightforward. Have we considered or tried adding a random element to it to make it a little bit more interesting, I'd say? No. Just because our designers really like predictability. And especially with adding a new feature that was completely new to the engine and actually new to our genre in that respect as well, we wanted to keep the random element out of it. But it's definitely something worth giving a shot. Yes. Okay, well, just for completeness sake, then Praetorians actually had a fire system that would spread fire in a little bit more simpler fashion. But okay, so I stand corrected. Yes. So the question is, have any fire expert commented on how realistic or unrealistic it is? Absolutely not, no. It is completely unrealistic. And please don't make any real-world assumptions on the outcome of the simulation. It's purely effect-based.
What was the resolution of the grid?
The question was the resolution of the grid. We actually ended up using the exact same resolution we were using for texturing the terrain. And it's the same resolution we use for the pathfinding. It's pretty much the same resolution for everything. So a typical map had about between 300 to 500 by 500 cells of these. And each cell is just a couple of bytes. So on the memory cost, for example, I think we ended up using about 3 megabytes, which on a PC is absolutely fine. All right. Well, I think everybody should head over to booth crawl now. That's it. Thank you very much.